Check. There. All right, so taking a look at a kind of a sampling question about resonance. And they want you to get all the way so that there's a negative charge on this oxygen. So resonance structures can be done in multiple moving electrons at once, or you can just move, a few at a time. You can do it stepwise, or you can do it all at once. I'll do it stepwise here, and then I can show you how to do it all at once as well. So I'll do it stepwise. So we move these electrons down. The pi bond electrons then would go to that carbon. So what would that look like? Some hints. When you're drawing these things, or any reaction or even resonance structures, draw what hasn't changed first, right? Remember, in resonance, atoms don't move. So draw the things that aren't changing first. All right, did I balance my charge? Yes, I have a negative charge there. So I balance my charge. I move the electrons all float in one direction. So I could do another resonance form here. This, of course, is stepwise. The electrons go to that bond. These electrons go to that carbon. Now we have the new pi bond there, negative charge there. And then the last move is just going to be pushing these there to form that pi bond, these electrons going up. Right? And that gets us to the final thing we're looking for. You could have also done this all at once if you wanted to. Right? You could have done this all at once if you wanted to. That's what they wanted you to get to. Now, if I want to do this all at once, I'm going to draw it with gold arrows. Something I would tell you not to do, draw over the top, but I'm going to do it anyway. Sorry. They'd go there. These electrons would go, instead of to the carbon, they'd go to that bond. These electrons would go there to form a new pi bond. And then these electrons would go up, and that would get you right here in one step. Those gold arrows would get you right there in one step. If I'm asking you for extra resonance structures, though, these are the kind of things I'd want. But you can get there all in one step as well. So the question here is, for each structure, determine the number of pi electrons and indicate whether it's aromatic, non-aromatic, or anti-aromatic. So this is one of those ones, kind of relating that hybridization state and how it relates to aromaticity. So the tricky part here is this lone pair is actually not part of the p orbital system. Right? This lone pair is in an sp2 hybrid orbital. Right? So it's not actually doing resonance here. So how many pi electrons are there? There's 2, 4, 6, right? Because every bond has how many electrons? 2. And there's 3 pi bonds, so 6 total electrons. Now, 6 total electrons, 3 pairs. When we talk about aromaticity now, we want to look for something that's conjugated, so an uninterrupted p orbital system. It's in a ring, and it has an odd number of pairs of electrons. How many pairs of electrons does this have? 1, 2, 3. That's odd. So this pyridine is aromatic. If you ever forget the rules, right? If you can remember just benzene, right? Just remember benzene. Benzene is aromatic. It's in a ring, it's an uninterrupted pi system, and it has odd number of pairs of electrons, right? So I always try to anchor myself back in something I know, and then look at it and to remember what aromaticity means. Now for this one, the cyclobutadiene, again, is it in a ring? Yes. Is it uninterrupted? Is it a p orbital system? Yes. How many pairs of electrons does it have? 1, 2, so 4 total pi electrons. But it has 2 pairs, so if it's odd is good, even is bad, this is actually anti-aromatic, right? With the even number of pairs of electrons. All right, so let's look at 2 other kind of little different examples. So this one, is it in a ring? Yes. Does it have an uninterrupted pi system? No. This nitrogen right, is what hybridization state? How many bonds does it have? It has 4 bonds, and they're all sigma bonds. Right? It doesn't have a lone pair, so this is actually sp3 hybridized. So there is 2 4 electrons in the p orbital system, but it can be aromatic because it's not an uninterrupted conjugated pi system. So this compound is actually non-aromatic, right? Non-aromatic. If the hydrogen was gone and had a lone pair, aromatic. It changes. What about for this one? Do we have an uninterrupted pi system? Yep, this oxygen is going to choose to be sp2 hybridized, have a p orbital with that lone pair. How many electrons are in the system? 1, 2, 3 pairs. It's an odd number of pairs. 6 electrons total, odd pairs, aromatic. Similar to the one over here, this lone pair is in an sp2 orbital, and one of these lone pairs is also in an sp2 orbital. But one's in a p orbital, and then part of the pi electron system, p orbital system.